At the bottom of the Mariana Trench, the pressure on every square centimeter of hull is equivalent to 50 commercial aircraft stacked on a human thumb. There is no margin, no warning, no second chance. The hull holds, or it implodes, faster than any instrument can record. In June 2023, a submersible called Titan descended toward the wreck of the Titanic. It never came back. 5 people, 1 catastrophic structural failure, instant annihilation at 3,800 meters depth. That is the world humanity has been trying to engineer its way into for 2,000 years. This is how we learned and how much it cost us. For 2,000 years, humanity has been descending into the most lethal environment on Earth. From Alexander the Great, lowering himself into the Aegean in a glass barrel, to the Bathysphere dangling on a cable in the midnight zone, to the titanium spheres of 2026 research submersibles, the engineering challenge has never changed. Keep the ocean out. Keep the human alive. Build a structure that can resist a force that has no interest in being resisted. At the bottom of the Mariana Trench, the water pressing against every square centimeter of a vehicle hull reaches over 1,000 atmospheres. There is no margin for error. A single hairline crack in a pressure hull does not leak, it implodes. The failure is not gradual. It is instantaneous and total. In this documentary, we trace 2,000 years of that engineering struggle. From trapped air and wooden bells, to vacuum-sealed syntactic foam, from hand-cranked iron hulls, to autonomous deep-sea robots, we reveal how humanity turned the most lethal void on Earth into an accessible scientific frontier. Before nuclear submarines patrolled the depths, before titanium pressure hulls descended to the ocean floor, brave and reckless engineers climbed into wooden barrels, hand-cranked iron tubes, and canvas-sealed diving bells and pointed themselves downward into a darkness that had killed everyone who entered it without protection. The ocean floor is not simply deep. It is actively hostile in a way that outer space is not. In space, the structural challenge is containing internal pressure against a vacuum. In the deep ocean, the pressure outside a submarine hull reaches over 1,000 atmospheres, a crushing force that increases with every meter of descent and never relents. The Titan submersible disaster of 2023 reminded the world what happens when that engineering fails. 5 lives, 0 warning. A carbon fiber hull that the deep ocean simply refused to accept. This is the story of 2,000 years of structural engineering against the weight of the world's oceans. Every advance paid for by the people who trusted their lives to the hull beneath them. How do you build a machine strong enough to resist a pressure that would crush solid steel like paper? The answer took 2,000 years, cost dozens of lives, and required humanity to abandon almost every engineering intuition developed on the surface of the Earth. On land, structures resist gravity. They are built tall, with weight flowing downward through columns and foundations. In the deep ocean, pressure arrives equally from every direction simultaneously. A box fails at its corners. A cylinder fails along its seams. Only one geometric form distributes compressive load perfectly across its entire surface, the sphere. That single insight, arriving after more than a millennium of failed attempts, changed everything. From the first sealed air pocket that kept a diver alive for an extra minute, to the bathysphere of the 1930s, to the Titan disaster of 2023, to the autonomous titanium vehicles, mapping the ocean floor in 2026. This is the engineering bloodline of the deep. 2,000 years of one question. How do you build something the ocean cannot crush? The first recorded attempt to breathe underwater was not an engineering project. It was an act of curiosity so reckless it bordered on suicide. Ancient accounts describe Alexander the Great being lowered into the Aegean Sea inside a sealed glass vessel, a primitive observation chamber that kept the water out through nothing more than the trapped air inside. The story may be partly legend, but the principle it describes is real, and was understood empirically long before anyone could explain the physics. Trapped air resists water pressure up to the point where the weight of the water column above compresses it beyond the volume of the vessel. At shallow depths, the compression is modest. At depth, it becomes lethal. The air compresses, the internal pressure rises, and the human body experiences the physiological consequences of breathing high-pressure gas long before the structural integrity of the vessel becomes the limiting factor. The physics of pressure with depth was not formally understood until the 17th century, but its effects were experienced by every diver who pushed beyond shallow water. The bends, The formation of nitrogen bubbles in the bloodstream as a diver ascends too quickly from depth killed free divers across the ancient Mediterranean without anyone understanding the mechanism. They knew only that descending too deep, or ascending too fast, was fatal. The engineering response was the diving bell, a rigid vessel, open at the bottom, lowered into the water with a pocket of trapped air inside. The bell worked because air, being less dense than water, remained in the upper portion of the vessel as it descended. A diver inside the bell could breathe that air, descend to working depth, exit briefly to perform underwater tasks, and return to the bell to breathe before ascending. It was not a pressure vessel. It did not seal against the ocean. It simply captured a volume of air and carried it downward, the same principle as inverting a glass in a bowl of water. Edmund Halley, the astronomer of comet fame, designed the first practical diving bell with replenishable air supply in 1691, using weighted barrels of fresh air lowered from the surface to extend the working duration. It was the first life support engineering for underwater operation, and it worked within severe constraints: depth limited by air supply, time limited by air quality, and the diver always tethered to the surface by the bell's lifting cable. The transition from diving bell to submarine required one fundamental insight. Instead of carrying air down to the diver, build a sealed vessel that the diver travels inside. The engineering challenge this created was entirely new. A diving bell is open at the bottom. It does not need to seal against water pressure because the trapped air prevents water entry. A submarine hull must seal completely against the ocean while simultaneously withstanding the external pressure trying to collapse it inward. The first practical submarine, David Bushnell's Turtle, deployed in New York Harbor in 1776, was a hand-cranked wooden sphere, caulked and sealed with tar, carrying one operator and enough trapped air for approximately 30 minutes of submersion. Its structural engineering was straightforward. The spherical form distributed compressive load more evenly than any other geometry, and the wood was thick enough to resist the modest pressures of harbor depth operation. It never achieved its military objective, but it proved the concept. Robert Fulton's Nautilus of 1,800 advanced the design. A copper-sheathed iron hull, cigar-shaped, with a hand-cranked propeller, and a collapsible sail for surface propulsion. The cigar shape was an attempt to reduce hydrodynamic drag, but it introduced structural complexity. The cylinder, unlike the sphere, concentrates compressive stress at its end caps, requiring reinforced bulkheads that added weight and manufacturing difficulty. Every early submarine builder confronted the same set of interconnected problems simultaneously. The hull must be strong enough to resist external pressure. It must be sealed well enough to remain watertight under that pressure. It must carry enough air to sustain its crew for the duration of the mission. And it must be propelled by a power source that does not consume the air supply. Hand-crank propulsion solved the last problem. Partially, human muscles consume oxygen, but at a known and manageable rate. The Confederate submarine H.L. Hunley of 1,863, hand-cranked by 8 men, iron-hulled, the first submarine to sink an enemy warship in combat, demonstrated both the potential and the lethal limitations of this approach. The Hunley sank 3 times, killing multiple crews before achieving its historic mission, and then sank again immediately afterward, killing its final crew for reasons that remain partially disputed. The engineering of the sealed pressure hull was advancing. The engineering of reliable, sustainable propulsion was not. The military submarine of the early 20th century solved the propulsion problem with electric motors powered by lead-acid batteries for submerged running, and diesel engines for surface propulsion and battery charging. This combination, still the basis of conventional submarine propulsion, today freed the hull from the constraint of human power and allowed submersibles to operate at depths and durations impossible for hand-cranked vessels. But military submarines were not deep-diving vehicles. They operated at depths of tens to hundreds of meters within the reach of surface weapons, within the range of human physiological tolerance, within the structural capacity of rolled steel pressure hulls. The true abyss, the midnight zone below 1,000 meters, the Hadal zone below 6,000, remained completely inaccessible. The engineering problem was not propulsion, it was geometry and materials. At abyssal depth, the external pressure exceeds 1,000 atmospheres. A cylindrical hull of any practical steel thickness would be crushed. The solution had been known mathematically for centuries. The sphere is the only geometric form that distributes external compressive pressure perfectly uniformly across its entire surface, with no stress concentration at corners, edges, or joints. William Beebe and Otis Barton realized this in the 1930s and built the Bathysphere, a cast steel sphere, 1.4, 5 meters in diameter, 3.8 centimeters thick, lowered on a single steel cable. In 1934, they descended to 923 meters, a world record that would stand for 15 years. The view through their fused quartz windows into the absolute darkness of the deep ocean was the first direct human observation of the midnight zone. The bathysphere was not a submarine. It could not maneuver. It hung on its cable, entirely dependent on the surface ship above. Auguste Piccard understood that genuine deep-sea exploration required free movement, a vehicle that could descend, maneuver, and ascend without a surface tether. His solution was the bathyscaphe, a steel observation sphere suspended beneath a large flotation hull filled with gasoline, which is less dense than water and incompressible at depth. The gasoline provided buoyancy. Iron shot ballast, released electromagnetically, provided the ability to ascend. In 1960, Piccard's Trieste descended to the bottom of the Challenger, deep 10,916 meters, with Jacques Piccard and Don Walsh aboard. It remains the deepest crewed descent in history. The pressure on the sphere at that depth was over 1,000 atmospheres. The hull held. The materials science revolution of the late 20th century transformed deep-sea vehicle design in the same way it transformed aerospace, by making available structural materials with strength-to-weight ratios. Impossible in conventional steel. Titanium alloys, with tensile strength comparable to high-grade steel at roughly half the density, allowed pressure hull spheres to be made thinner, lighter, and capable of surviving greater depths without the weight penalty that limited earlier designs. Carbon fiber composite materials offered even greater strength-to-weight ratios for non-pressure-bearing structural components, fairings, frames, syntactic foam housings. Syntactic foam itself, a composite material of hollow glass microspheres, suspended in epoxy resin, provided buoyancy at depth without the bulk of gasoline flotation tanks. The microspheres resist compressive pressure without collapsing, giving the foam a density lower than water even at abyssal pressures. Modern research submersibles like Alvin, Deep Sea Challenger, and Limiting Factor carry their buoyancy in syntactic foam blocks that make up the majority of their visible volume. The science they have enabled is transformative hydrothermal vent ecosystems, discovered in 1977. New species cataloged in the thousands. Seafloor geology, mapped at resolutions impossible from surface vessels. But the engineering of deep-sea vehicles remains unforgiving of error. In June 2023, the Titan submersible, operated by OceanGate to carry paying passengers to the wreck of the Titanic at 3,800 meters depth, imploded catastrophically during its descent. All 5 people aboard were killed instantly. The investigation identified the hull construction as a critical factor, a carbon fiber cylinder joined to titanium end caps, a combination that subjected the joint between dissimilar materials to cyclic stress with every dive. Carbon fiber, unlike titanium or steel, does not exhibit the gradual fatigue warning signs, visible deformation, acoustic emission that allow engineers to detect approaching failure before it occurs. It fails suddenly and completely. The Titan disaster was not simply a tragedy. It was a structural engineering failure that the deep-sea community had warned about, a reminder that the abyss does not grant second chances, and that the margin between a functioning pressure hull and instant annihilation is measured in material science, not optimism. As of 2026, the frontier of deep-sea engineering has shifted from crude exploration vehicles to autonomous systems, remotely operated vehicles, and autonomous underwater vehicles that can operate at abyssal depths indefinitely, without life support constraints, without the structural compromises required to keep a human being alive at pressure. A fully autonomous deep-sea robot does not need a pressure hull rated for human survival. It needs only to protect its electronics and power systems, a far less demanding engineering requirement that allows smaller, cheaper, more numerous vehicles to map and sample the ocean floor at scales previously impossible. The data they return is transforming ocean science high-resolution bathymetric maps of the entire seafloor, real-time monitoring of hydrothermal vent activity, continuous sampling of deep ocean chemistry. But the engineering ambition does not stop at robots. Modular titanium habitat systems, permanent underwater research stations anchored to the continental shelf at depths of tens to hundreds of meters, are being designed for long-duration human occupation. The life support engineering of these habitats draws directly on the lessons of 2,000 years of submarine development, sealed pressure hulls, atmospheric management systems, emergency ascent protocols, and structural monitoring that provides continuous early warning of seal degradation or hull fatigue. The deepest ocean is also serving as a test environment for something far beyond Earth. The subsurface oceans of Europa and Enceladus moons of Jupiter and Saturn, respectively, are believed to contain liquid water beneath kilometers of ice at pressures and temperatures comparable to the deep terrestrial ocean. The engineering challenges of building a vehicle that can survive those environments, penetrate the ice shell, and operate autonomously in a subsurface ocean, billions of kilometers from any repair facility, are being developed through the deep-sea exploration programs of 2026. The ocean that killed the crew of the Titan, that crushed the diving bells of the 17th century, that drowned every engineer who underestimated it, is now the training ground for the machines humanity will send to look for life in the oceans of other worlds. 2,000 years from Alexander's glass barrel to a titanium sphere on Europa, the abyss has always been the proving ground. It remains so.